Hello and welcome to this screencast that is going to serve as a basic walkthrough/review for the first third of our course, namely chapters 2 through 5. And I want to take the some of the aspects of our first exam to then walk through some of the key points that I hope we were able to get out of this course so far as a foundation for moving forward. Early on in the course, we talked about different ways to organize data, and on this exam one, we had to take some data that was in an Excel format here, and they were set up to be test scores for students for exams 1, 2, and 3. And we were looking for us to be able to categorize them based on the grade levels of A, B, C, D, and F, and basically take then a count of how many in each of the exams, how many test scores fell in these different ranges, and then produce what is called a histogram for each of these. So these were the histograms for exams 1, 2, and 3 from exam 1, if we broke them up into the grade levels that we were looking for of, again, A, B, C, D, and F. And you can see here from taking a look at the three of them, there's some similarities and some differences. So for example, exam 1, and you can see that it is not necessarily symmetrical, that the bulk of the scores were up in the upper levels of A, B, and C. And then there were a few maybe outliers or a few elements down here in D and F. So this would be categorized as not a normal distribution, but one that is skewed and skewed left, or negatively skewed. The skewness is always towards the tail, where the fewer the items are. Exams 2 and 3 were both pretty symmetrical when we broke them up by these grade levels. Some of us didn't break them up into these grade levels and broke them up even finer into more classes and ended up not coming out looking as symmetrical as these were. But as symmetrical as both exam 2 and 3 are, you can see that exam 2 has values that are a little bit more spread out, whereas exam 3 had the majority of the items here in the C range and fewer in the A and F range. And that can be then noticed here in the listing of the different descriptive statistics that we found. So we have the mean of an 85, for example, in exam 1, and a median of 88. So the two of them were not identical. And that tends to be the case when we have a distribution that is not symmetrical. So the more skewed the data is, like it was here in exam 1, the further the mean and the median will be apart from each other. And you can see here that the median was greater, and that will be normally the case, where the mean is being pulled down by the outliers or the values that are in that tail. And the median was up in the higher end of the 88. So the more or the further these 2 points would get away from each other, the more you can expect the distribution to be skewed one direction or the other. Down here in exams 2 and 3, you can see that they are symmetrical, and that's reflected here also in the mean and median of each. Both of them have a mean and median of 81. So again, the closer these values are to each other, the more you can expect them to be symmetrical. The further they are away from each other, the more you can expect them to be spread out or skewed and not symmetrical. The third thing I want to point out here for these is the standard deviation. And the standard deviation is a measurement of how spread out the values are. And so the greater the standard deviation, the greater the spread. And if you take a look at exams 2 and 3, when you look at the histograms, you can see that they are both symmetrical, but exam 3 has values that are tighter together, closer to the mean. And that's reflected here in the fact that the standard deviation for exam 3 was a 7.14, which is smaller than the standard deviation here for exam 2. So again, going back on that, standard deviation is a measure of spread, or how spread out the values are. And we have on the surface 2 exams that look very similar in the fact that the means were both 81 and the medians were both 81. But when we take a look at the standard deviation, we can see that this one had a lower standard deviation, which means that exam 3 had a set of data that was tighter to the mean. And that's reflected here on the histogram. So that was the first 3 major sections in the course. And I'd like to then take a look at how these were used for Chapter 5. I'm going to skip over here to the to this chart. Now, Task 5 from the test is very synonymous to Chapter 5 in our course, where we are using the normal curve and the mean and standard deviation to make predictions about a population. Now, right now I have a lot of clutter here in this work, but I'll try to walk through it carefully. The 2 of the problems in Task 5 dealt with Test 3. So one of them, for example, said, determine the proportion of population you would expect to score 84 or less. We needed to define the proportion of the population that we expected to perform 84 or less. The first thing we need to do is to get the mean and the standard deviation that we calculated previously for Test 3. So Test 3 had a mean of 81.05. Again, I'm taking it from here. And I had a standard deviation of 7.14. So we're going to use those as our foundational elements for this. To solve this problem, we needed to take a look at this normal curve. The normal curve is spread out so that it's symmetrical, with the mean at the center here at 81.05. And each one of these tick marks going out from the center here represent one standard deviation. So I put in here in black the illustration of me going out one standard deviation from the mean. So 81.05 was our mean. I added 7.14 to that to then get the value of this next tick mark of 88.19. And then you can do the same thing in reverse by subtracting that amount repeatedly going down. And on a normal curve, you can see that the bulk of the data is going to be clustered about the mean. And the further you go out towards one of the tails, the less likely you have data points out there. And again, that kind of matches what we have right here for this histogram. Now for this problem, what we need to do is 2 steps. First, we have to find out where does 84 lie on this normal curve. And instead of trying to plot it and guess where it is between an 81 and an 88, we convert everything to z-scores so that it's normalized. And we use this formula here where we subtract 84, which is the value that we're looking at, minus 81.05, which was the mean. We get a difference between those, and then we divide by the standard deviation. And that gave us a z-score of positive 0.413. That tells us then that we are 0.413 standard deviations above the mean, right in this range here. Then we have to take a look at the table in the back of the book, Table A, and we have to find out what is the area under the curve, or the proportion of the population that falls between that z-score in either the center or the tail. And that's where you're going to have to use the judgment of what the problem is. For this problem, we're looking for what's the proportion from 84 on down, or 84 or less. So we need the area under the curve from a z-score of positive 0.413, which is roughly around here. We need the area from this value all the way to the tail. We're looking at less than 84. Now, our table in the book does not give you the area from a point of one side of the mean to the tail of the other side of the mean. So what we need to do is use the column in the middle, column B. We need to find the area from this value to the mean. So I go down the z and find a positive z-score of 0.413. I find that row, and then I cut across to the right to the next column, and I see that I have an area of 0.1591. That is the area from this value which was our z-score, to the mean, right here, the area of this region. That area is the proportion of the population that falls between an 84 and our mean. But we need from 84 on down past the mean all the way to 0. So what we need to do is to take that area under the curve and then add to it another 0.5000, which is the area from the mean to the tail. We add those two together, and that gives us a final proportion of 0.6591. Again, this is in the value of, or the unit of a proportion. The proportions always need to be between 0 and 1. And then when we convert them, if you want to the percentage, then it's basically saying we can expect roughly 65.91% of the population to fall from 84 on down or less. So that's how you do that problem. The other type of problem is when we have the reverse scenario. Instead of us having the actual cutoff score that we want and us finding the proportion of the population from one side or the other, instead, the next problem said, the teacher provides a list of students who score in the top 15% of the population to the dean for an award. If the teacher uses test 3 for this award, what grade should be selected as the cutoff for the award? So for this problem, we're looking at where is the cutoff on this graph with this mean and standard deviation such that wherever that cutoff is from the area from that value to the right tail is the top 15% of the population. So now again, we're doing this in reverse. We don't have the score and then trying to find a proportion. We actually have the proportion now and we're trying to find the score. So 15% converts to 0.1500 as far as the proportion is concerned. And we're looking for that top 15%. So we can shade in brown here the portion of this tail that has a value of 0.15. And again, I'm just guesstimating it here. So it's not like I know that this area is 0.15. But I'm doing it for a visual to help myself lay this out. So I need to find the test score, the cutoff score, such that when I find that location, the area from here towards this tail is 0.15. So I have to use the table in the back in reverse. I have to go down the column that shows an area from a value towards the tail, which is column C, and I have to find a value that's closest to 0.15. And I scroll, I go all the way down the line and I find this one here, 0.1492. That was the value that I found to be closest to 0.15. And the z-score that led me to that, if I take a look at this value and then move to the left on the table, it gives me a positive z-score of 1.04. I know it's positive because my value, in order to be the top 15%, must be higher than the mean. Since it's higher than the mean, it must be a positive z-score. If they asked me for the bottom 15%, it would be the same exact curve or area under the curve, but on this side, and I would have a negative z-score. Now the last step is to take this z-score, use the formula that we had for z-score, but break it up and use it in reverse. And in chapter 5, they lead you through this, but let's talk through it again. I need to find then the value. What I do then is I take the mean and I add to it the z-score times the standard deviation. So the 81.05 came from here. The z-score came from the table in the back of the book. And the standard deviation came from my data set also. I plug all these values in, use the formula, and I end up with a value of 88.48. That is the test score on test 3. That would be the cutoff grade, such that all the values above would be in the top 15%. All the values below would not be. I hope that helps kind of review some of the topics that we've covered the first third of the year. And if you have any questions, let me know, but I look forward to moving on to phase 2. Thank you.